Hi guys, and welcome back to my channel. In this video we'll be going over the equipartition theorem, and this is basically going to be an extension of my previous video that was deriving the kinetic energy for monoatomic ideal gases. So if you haven't watched that video, you should watch that video first to understand how we got to the final formula. And this video is going to be extending that knowledge to diatomic and polyatomic gases, right? Because we're not only interested in monoatomic gases, we're also interested in the gases in our atmosphere that are polyatomic, like water molecules or carbon dioxide or nitrogen. How can we take the kinetic energy formula that we derived, right, for just a monoatomic gas and extend that to a polyatomic gas that might be more useful to do analysis of, right? So that's what this video is going to be about. So let's get right into it. So in this slide, I just want to recap what we learned in the last video, and that was that kinetic energy equals 3/2 kBT for a monoatomic ideal gas, right? This was our kinetic energy formula, and I've written it a little bit differently in on the slide. You can see I pulled out the 3 and I wrote it as 3, and I've bolded the 3 because the 3 is important, times 1/2 kBT. So I just want you to note this number 3, right? I talked about it in the last video that this 3 is an important number and it has something to do with the gas. And it is called actually the number of degrees of freedom of the gas, and I'll get into that later in this video. So how did we actually get this 3, right? We got it from just the nature of the kinetic energy formula. So we know that kinetic energy equals half mv squared, right? This is the formula for kinetic energy. But remember that we could decompose v, our velocity vector, into the 3 components of motion. And the velocity vector can be, because it's in 3 dimensions, can be decomposed into the x component, the y component, and the z component. And that is exactly what we did here, right? By Pythagorean theorem, we know that the average value of v squared is the same thing as average value of vx squared plus vy squared, plus vz squared, right? Exactly the substitution that I made on the slide. And remember that there's nothing special about the x, the y, or the z direction. I could define, I could swap these directions around and nothing would change, right? Because x, y, and z are just arbitrarily defined. There's nothing special about any of these directions. So when I take the average over all of these directions, they should be basically the same. The averages in each direction should statistically, right, be the same, because nothing is special about any one direction. So what I could do is I can just write this sum as just 3 times vx squared, or 3 times vy squared, or 3 times vz squared. It doesn't matter, right, because they're all the same. But here again, you can see that we have that 3 coming into play, and so this is why I want you to note this is where we actually got the 3, because we had this x, this y, and this z direction that basically contributed the same thing to the kinetic energy, right? If you think about this, we can, if I FOILed it out, if I expanded it out, the kinetic energy can be written as half m v squared, vx squared, right? I can do half m vx squared plus half m vy squared, and then, plus half m vz squared, if I just expanded this formula out, right? And you can see that the vx direction, the vy, and the vz are contributing equal amounts to the kinetic energy of the gas, right? So this is kind of important. We see that vx, vy, and vz are contributing equal amounts. You might be thinking equipartition, right? And I'm going to define this in the next slide after this, but I want you thinking that we're sort of equally partitioning the kinetic energy between 3 different directions of motion: the x, the y, and the z directions of motion, right? So this is sort of to get you thinking about what's to come in this video. So let's go on to the next slides and we'll talk more about this. All right, so this is the equipartition theorem slide, and I'm actually going to define what I mean by equipartition theorem and talk about this more, right? So you might notice that, remember, each of the terms in the kinetic energy equation contributed half kBT. So if I rewrite what I wrote on the previous slide, remember we had half m vx squared plus half m vy squared, and finally a half m Vz squared. Right, this was our total kinetic energy formula, and we know that this also equaled 3 halves kBt, and I'm going to write it actually as 3 times half kBt, right? But each of these components were equal because these averages were equal. So that means each of these components must give half kBt, right? So each of the terms in the kinetic energy equation contributes half kBt to the total energy. And thus, the total energy, when we sum up the 3 components of the x, y, and z components, is equal to 3 halves kBt. So these are called quadratic contributions. So this like half mvx squared, this half mvy squared, this half mvz squared, these are quadratic contributions to the kinetic energy. And what is a quadratic contribution? That just means that it's a contribution to the total energy, right? Obviously, because this is part of our kinetic energy equation, and it depends on the square of the velocity. This depends on the square of the velocity. We have vx squared, vy squared, vz squared. So all of these terms are called quadratic contributions. Now let's talk about the equipartition theorem. And here I'm just reminding you of what I sort of wrote down above. Let's talk about the equipartition theorem, and this is the big thing in this video. All quadratic contributions to the total energy have the same mean value that's equal to half kBt. And this is basically what I showed up here, right? When I was talking about this formula, is that vx squared, vy squared, vz squared, that's the exact same, they're all the exact same things once I average it, right? Because there's nothing special about any of these directions. So each of these guys, because this is equal to 3 times 1 half kBt, each of these guys must contribute half kBt. So all of these quadratic contributions have the same mean value, right? Because this is the average. They have the same mean value of half kBt, which is exactly what we showed up here, right? Because there's nothing special about any of these directions. But this is going to get more important because we're going to talk about not just, translational motion, which we've been talking about. This is the same thing as with a monoatomic gas, right? I've been talking in the context of monoatomic gases, where we just have the same exact formula that we derived in last class, or last video, where I have the x, the y, and the z direction, and that's all I'm worrying about. These translational directions of motion, right? But when we talk about rotational and vibrational degrees of freedom, and I use that word degrees of freedom, that's just another word of all available modes of motion. So, but when we talk about these vibrational and rotational factors, we can also use the equipartition theorem for those and realize that they contribute half kBt as well. So this is sort of an important realization, and this is the heavy-hitting, idea of this video that I want you to take from it. Okay, so now let's talk about degrees of freedom. Degrees of freedom is just defined as all available modes of motion. So let me connect degrees of freedom to quadratic contributions. Basically, you need to find the total number of quadratic contributions if I want to find the total kinetic energy, right? So how do I do this? Each of these contributions is given by a degree of freedom. So one quadratic contribution, if I write this, one quadratic contribution is basically given by 1 degree of freedom. So let's talk about this with the monoatomic ideal gas case. You can see we have half mvx squared. That's one quadratic contribution. And we note that we're only taking the velocity in the x direction. So that's an x direction translational motion. So the degree of freedom, that's related to this quadratic contribution is x translational motion. Translational motion. If I look at the half mvy squared, this is another quadratic contribution. This is y translational motion. And then half mvz squared is z translational motion. So each quadratic contribution is basically given by a certain degree of freedom. Okay? So that means that this multiplier of 3, right? That is given by the number of degrees of freedom in a monoatomic gas. Because the number of degrees of freedom tells us how many of these quadratic contribution terms we're summing up, right? And the number of quadratic contribution terms we're summing up equals this multiplier out in front. Because every quadratic contribution gives half kBt, right? So the multiplier to half kBt is the number of degrees of freedom. And that's why I wrote our kinetic energy formula as 3 times half kBt, because that 3 is the number of degrees of freedom of our gas, right? So that 3, again to stress it, is the number of degrees of freedom in a monoatomic gas. The next slide is going to be how do we extend this idea to polyatomic gases, right? This 3 is degrees of freedom in a monoatomic gas. How do we take that and figure out the degrees of freedom in a polyatomic gas? So let's move on to the next slide. Okay, so this is the slide on degrees of freedom, and where we're going to think about degrees of freedom in not just monoatomic gases, but polyatomic gases. Each atom in a, so first let's find the total number of degrees of freedom, right? And I'm going to say, just tell you that the total number of degrees of freedom is 3n, where n is the number of atoms. And how can we, justify this? Each atom in a molecule, right, if we think about, any molecule, let's just do CO2. I'm just going to draw it. Each atom in this molecule can move in the x, the y, or the z direction, right? And there's three possible directions it can move, right? Because it's in 3D space. Each atom can move in 3 possible directions. There's n atoms. So the total degrees of freedom of this molecule is going to be 3 times n. Because 3 comes from the 3 directions each atom can move. N comes from the number of atoms. So we have 3n total degrees of freedom of this molecule, right? Okay. Now let's break these total number of degrees of freedom into translational, rotational, and vibrational. We've talked about translational a bunch, right? We've talked about motion in the x, y, and z direction. And let's look at our formula with a monoatomic gas, right? With a monoatomic gas, we get that the total number of degrees of freedom is just 3. And all of these 3 degrees of freedom are given are put into the translational category. Because every particle, right? Every molecule or atom has to move, right? Any particle has 3 translational degrees of freedom. No matter if it's a monoatomic gas, a polyatomic gas, or I've broken it down into categories here, polyatomic linear or polyatomic nonlinear. So no matter if it's monoatomic or polyatomic, right, we have 3 translational degrees of freedom, because that comes from just the x direction of motion, the y direction of the motion, and the z direction of the motion of the entire molecule. So note, I'm not talking about the atoms now, right? I'm not talking about each individual atom, like how I found the total number of degrees of freedom. I'm talking about the molecule or particle as a whole, and it must have 3 translational degrees of freedom at all times, because it can move in the x, y, or z direction. It can move in 3D space, right? So for any particle, any particle has 3 translational DOFs, degrees of freedom. And you can see that in my little table here. My translational, if I look in the row of translational degrees of freedom, you can see that I have 3 for every single type of molecule. And I'll show you exactly why I broke it down into these 3 categories. But you can see that translational, there's always 3, because I can move in the x, y, and z direction. But for molecules that have more than one atom, right? For when I'm looking at polyatomics, there also are degrees of freedom that come from there are degrees of freedom that come from rotation and vibration, right? There's a rotational and vibrational degrees of freedom, right? And if I look at my total number of degrees of freedom formula, right? Say I have a molecule where n equals 2, so I have 2 atoms. 3n gives me 6 total degrees of freedom. But I know I only have 3 translational. I only can move in the x, y, and z direction, right? But the other degrees of freedom are my rotational and vibrational. So let's talk more about rotation and vibration, right? Basically, these rotational and vibrational degrees of freedom can contribute to the energy. Remember how we said each degree of freedom contributes half kBt. Rotation and vibration, these sort of forms of energy also contribute to the kinetic energy of a gas molecule. So for just like, think about this intuitively. If I had a little, you know, a linear molecule that was just two atoms, right? I can move in the x, y, and z direction, and those take energy, right? That I need kinetic energy to move. So this motion in the x, y, and z direction takes kinetic energy. And so of course this motion is going to contribute to my kinetic energy. But also, I can rotate like this, right? I can rotate like that. Or I can rotate into the plane of the page, right? Another way to rotate is into the plane of the page, right? I can rotate into the plane of the page. I can rotate in the plane of the page, right? And these sort of motions are going to take kinetic energy, right? This motion is going to contribute to my kinetic energy, the fact that I'm rotating. And finally, right, what's another thing I can do? If I have a chemical bond, this is like a bond, it can vibrate, right? I can compress and then I can expand, because chemical bonds are like springs. And the spring compressing and expanding is basically a vibrational degree of freedom, right? That's going to contribute to the energy as well. So you can think about this intuitively, like translation is not the only thing that's going to contribute half kBt to my kinetic energy. So how do I account for this, right? We can just find the number of degrees of freedom of rotation and number of degrees of freedom of vibration. So let's look, and we're going to break this down into polyatomic linear and polyatomic nonlinear, and I'll explain why we're breaking it down in a second. Let's look at a linear gas first. So let's look at something like nitrogen, right? We have nitrogen that looks like this. Now, how can this rotate, right? This can rotate, if I think about it, like around, there's three axes, right? There's the x-axis, the y-axis, and the z-axis. So we can have rotation around the x-axis, rotation around the y-axis, or rotation around the z-axis. Now let's look at all those possibilities, right? This is the x-axis. So this is the most important one that I want to rule out, right? If I do rotation around that x-axis, which goes straight through the bond, right? What is that doing when I rotate around the x-axis? That's doing nothing. Right? Because I'm basically, if I try and rotate around this axis, I get the same exact thing back. There's nothing that's happening, right? So there's no rotation around x-axis, because I'm getting the same exact thing back when I, like, quote unquote rotate, right? If I spin this, there's nothing that's changing, so I'm not really rotating. So this x-axis is not actually, this rotation around the x-axis is not actually a degree of freedom for a linear molecule, right? And that's why it needs to be linear for this to be true, because I need to find a axis that goes straight through my bond. So if I think about like CO2, for example, if I pick the x-axis like that, and I rotate around that x-axis, again, there's no rotation that's really happening. So, but let's look at the other two axes, right? If I don't look at this x-axis and I look at the y-axis now, y-axis, I can totally rotate around this y-axis. That means this guy would go into the page, this guy would come out of the page, and that's a valid rotation. So that gives 1 degree of freedom. And if we looked at, the z-axis, that would also give another degree of freedom, right? If I looked at the z-axis like that, that would also, I would be spinning up and spinning down, right? So you can see that these are valid sort of rotations, and each of these rotations are going to contribute 1 degree of freedom. So we have the y-axis and the z-axis. But note that the x-axis doesn't do anything. And I'm giving these labels sort of arbitrarily, it doesn't matter. But in how I was talking about it, I said the x-axis was the axis that went straight through the bond, and that's what matters. Rotation around that doesn't really cause any, it's not really a rotation, right? It doesn't cause any change in the molecule, so we're not really rotating. And the only valid ones are the y-axis and the z-axis, and each of these are 1 degree of freedom. So the total rotational degrees of freedom is going to equal 2. And you can see that's what I wrote in the table, right? And with polyatomic nonlinear, we don't have this problem. Right? Let's just draw out a molecule like water, for example. Right? There's no bond, there's no sort of axis that I can draw that this molecule will not be able to rotate around. Right? I can draw every axis possible, x, y, and z axis, But my water molecule can rotate around all three of them, right? There's no like problematic things like when we had a linear with an axis going straight through the entire molecule, right? All of the bonds of the molecule. Like with this guy, right? There's no problems like that with water because we can't have an axis that goes straight through the entire molecule because the molecule isn't linear, right? And of course our axes are linear, so we don't have this problem. And we can rotate around x, y, and z axis, which gives us 3 degrees of freedom. And here, that's why we have a 3 in this table for 3 rotational degrees of freedom. And finally, let's talk about vibration, right? Vibration, we basically find vibrational degrees of freedom by knowing that the total sum has to be 3n. So remember this. The total number of degrees of freedom has to equal 3n. And we know the translational and rotational degrees of freedom. So we basically say, okay, the sum of everything has to be 3n. So what does the vibration need to be? So if we have 3 translation and 2 rotation, and the sum needs to be 3n for everything, we know that vibration needs to be 3n minus 5. And if we do the same thing for the polyatomic nonlinear, we know that we have 3 translation and 3 rotation. So 3n minus 6 needs to be the number of vibrational degrees of freedom so that we have a total number of degrees of freedom of 3n. Okay, so one thing that's important is that at normal temperatures, so at semi-normal, I'm going to say normal temperatures. So this just means like temperatures that are even close to room temperature, right? Not like super cold or super hot, right? At these normal temperatures, only translational and rotational degrees of freedom play into the kinetic energy. So only, this is important, translational and rotational play into sort of affect kinetic energy, right? So if I'm looking at the kinetic energy formula for, let's look at the monoatomic gas first. And just go into the other ones, right? At normal temperature, the formula for the kinetic energy will be 3 times, parentheses, half kBt, right? Because we have 3 degrees of freedom. This is exactly what we talked about before. If we look at the polyatomic linear case, at normal temperatures, we're only looking at translational and rotational because vibrational doesn't play into these degrees into kinetic energy at normal sort of anything remotely close to room temperature. So for polyatomic linear, we would have 5 times half kBt. Because remember, each degree of freedom contributes the same half kBt to the kinetic energy, right? And we have 5 total degrees of freedom, so we have 5 times half kBt. If we have polyatomic nonlinear, then we have 6 total degrees of freedom that matter in terms of being translational and rotational. So we have 6 times half kBt. And I'll explain why translational doesn't matter, or quote unquote doesn't matter at normal temperatures in the next slide. We're going to talk about the sort of quantized nature of these degrees of freedom. Okay, so I just wanted to give you an idea of why I said the vibrational degrees of freedom don't really matter at normal temperatures. And show you, these degrees of freedom are quantized in this sense, right? They're quantized. And this sort of might tie back into a little bit of how you were thinking in the first chapter when we talked about the quantum nature of a lot of things. We talked about how there's sort of like minimum energies necessary, right? We talked about how to excite an electron from one state to the next state, there's this sort of minimum energy you need to apply to that electron, right? So that it jumps up energy levels. And we sort of have the same way of thinking with these degrees of freedom, right? There's this sort of minimum energy that we need to unlock degrees of freedom. So essentially what I mean to say is that there's a certain minimum energy. So there's a minimum energy needed to excite a molecule and to unlock degrees of freedom. So we need some sort of certain minimum energy to unlock these degrees of freedom. And how this energy goes is to unlock vibrational. So the energy for vibrational, to unlock vibrational, is much greater than the energy we need to unlock rotational. And this is greater than the energy we need to unlock the translational. Okay, so let's look at this sort of image. Let's look at this graph, and let's understand what it's showing, right? So we see that we have temperature on the x-axis here. So we're increasing the temperature, and by increasing the temperature, we're sort of adding energy into our system. So as we go to the right, we're going to add energy, and we can unlock more of these degrees of freedom. And on the y-axis, we have this thing called CV, and I'll talk more about this when we go into thermodynamics. But you can see that we have these values: 3 halves, 5 halves, and 7 halves. And you can see that we have R. R is basically the molar equivalent of the Boltzmann constant. Remember, R over Avogadro's number is the Boltzmann constant. So basically, I wanted you to think about these values as 3 times half kb, 5 times half kb, and finally 7 times half kb. Okay, this is how I want you to think about these values. And now you can see more clearly the degrees of freedom that are sort of coming out, right? We can see that here we have 3 degrees of freedom, here we have 5, and here we have 7. And the 7 is an interesting one, and we'll get to it later. But I wanted to show it like this to see where the degrees of freedom really, came. Okay, so at the very beginning we have cold temperatures, 10 to 100 Kelvin. You can see that our number of degrees of freedom that are unlocked is 3. Oh, and also this is for the hydrogen gas, which looks like H2, right? So this is a polyatomic linear molecule. That falls into the polyatomic linear case. So at normal temperatures, we would have, remember, 5 times 1/2 kBt as our kinetic energy, right? Because we have 3 degrees of freedom from translation and 2 from rotation. And the vibration usually doesn't matter, right? But you can see at really cold temperatures, we have only 3 degrees of freedom that are unlocked, only translational, because we haven't reached that sort of energy rotational barrier. And next, you can see we get to more normal temperatures, right? This is like, a little bit over 100 to basically 1,000 Kelvin, which is super hot, right? So this is like the normal temperature range. You can see we've unlocked rotation, and we still have our translational. So we have our kinetic energy being given by 5 times 1/2 kBt, and that's what we're used to, right? This is what we showed in the previous slide. But then once we increase our temperature even more to in the range of 1,000 to basically 10,000 Kelvin, which is super, super hot, right? We unlock our vibrational degrees of freedom. So our kinetic energy formula changes a little bit. It's not 5 times 1/2 kBt anymore. It's 7 times 1/2 kBt, right? So because we basically unlocked these vibrational degrees of freedom, and that's why we have our curve increasing even further. So I just wanted to mention, why we have this sort of quantized nature of degrees of freedom, and we have to unlock these degrees of freedom by increasing the temperature and adding more energy into the system. So that was what was important with this slide, right? It's not to say that we don't want to use the rules we sort of followed in the previous slide, but it's to show that degrees of freedom have to be unlocked. There needs to be energy inputted in the system to unlock degrees of freedom. And rotation needs to be unlocked. Translation is sort of the bare minimum. We unlock the rotation, then we finally unlock vibration. And at normal temperatures, that what we're worried about, we want to include translation and rotation. And lastly, you might be wondering why there's a 7 in front of the degrees of freedom for vibration, right? Because remember, when we talked about a polyatomic linear molecule, we said that the total degrees of freedom should be 3n, right? I mean, for any molecule, the total degrees of freedom should be 3n. So if I wanted the number of vibrational degrees of freedom, that should be 3n minus 5. for hydrogen gas, right? So that should give me 1 vibrational DOF, right? But you can see instead of being 6 over 2r, we have 7 over 2r, which is weird, right? So why is 1 vibrational degree of freedom giving an increase in 2 times 1/2 kBt, right? Instead of just 1/2 kBt. And that's because when we have vibration, we have energy being stored as potential energy when we compress the springs, and kinetic energy by the motion of the atoms in the spring, right? So there's sort of these two factors coming in, is the potential energy of squishing the spring together and the kinetic energy of just the motion of the atoms on the spring. And so we actually contribute 2 times 1/2 kBt. But this is not really important because we never have to actually worry about vibration when we're doing calculations, especially for Olympiad problems. You'll never have to worry about vibration because we're thinking about temperatures in this range where we have translation and rotation. Okay, so that's all I wanted to cover in this video. I hope it was informative. Thank you guys so much for watching, and I'll see you in the next one.